It's now to discuss about passive devices and simulation and measurement in regards to wide bandgap devices. We know that switching speed is quite higher, and that's quite challenging for capacitors, for inductors, for the materials there, and for the measurement tools to run it efficient. So now we are open to take questions from the auditorium to the specialists. I see there is
Yeah,
no
it's
question
rightly
yet.
corrected, as you say, Guru.
JC, you have a question? Or
Yes, I would like to make a remarks because as correctly as you pointed out, people think that the frequency is going up and probably is going to shrinkage the size of the magnetics. The problem is that actually there's hardly any validation technique in the standard. And therefore, I would like to point that out and to get aware about the audience. There are still a lot of things still not very understood. And once the magnetics not get done, nothing get done. And that's the key message I would like to bring this to the conference.
okay. Simon, about measurement at higher frequency. It's one of your expertise.
Yes, of course. Let's say, with respect to the standardization bodies, I agree to what was said. JC70 is, of course, so the JEDEC consortium, way beyond, let's say, of having finished measurement procedures for all applicable kinds of characterization techniques being used in wide bandgap modeling and device characterization. And at high frequency, it's basically if you measure a high power device, you have to, how to say, down convert voltages and currents to protect your VNA and other high frequency measurement equipment. And let's say in these kind of measurements, it's always, how to say, the most critical thing where you have your calibration plane, basically which parasitic effects you consider in the measurement, let it be TDR, let it be VNA, whatever, double pulse test. It doesn't matter, but which one you always need to model somehow the test fixture. The alternative would be you assemble your device under test package in a way that according to the, let's say, functional device, you have also a calibration device offering you open, a short, a load calibration that you can de-embed basically the parasitic effects of the package, or you want to include them in the device characterization, but you have to mount the package, so you have then to have a PCB test fixture somehow offering you a salt calibration. And this is, I would not say challenging, but it's expensive.
Okay, thank you, Simon. I got a question in which I want to address to all of you. I'm not quite sure who should exactly Pickett, what are the EM settings requirements for accurate 3D EM simulation of power electronic systems? Momentum, RF-microwatt, FEM question, classic ports or differential ports, frequency range. So thank you in advance.
So
It's more
I can
than one
answer that.
question.
I can answer that because momentum RF and microwave FEM is maybe relating to the simulators being available in PE Pro, which is one of the simulators used in the paper I've
Simon,
presented.
you are very, can you adjust your microphone, or it's hard to hear you.
Better now?
Now it's better.
Yeah, okay, then I come closer. So I want to answer the question, let's say, classical ports or differential ports and the solver and the frequency range. So the frequency range you can really determine by the minimum of the rise time you want to resolve, basically the ripple frequency you have, the switching frequency you have. And so just to apply a rule of thumb here, it's 0.35 to the minimum of rise time, number of harmonics multiplied. And we have implemented that in our tool so that it automatically covers it. To give you an example, if you have some kilohertz ripple frequency and switching frequency of maybe a megahertz, then you should simulate up to a gigahertz or so. For the ports, let's say, you can, for instance, apply differential ports when you have a series shunt a series inductor, or then other port type when you have a parallel shunt. But let's say the port itself just need to be aware of the self-inductance. So you need to have a port type where you can de-embed the port inductance. And this determines basically whether you use a solver like FEM, where you can better do that, if you have respective 3D structures. So if you are missing a solid ground plane, what often is the case in power electronics designs, you should use FEM, that you have proper port geometry, for instance.
Thank you, Simon. There is another question addressed to your site. That you give the auditorium your opinion on what is still missing for wide, broad use of virtually prototyping in power electronics. And do you see any difficulties in terms of modeling of wide bandgap power electronic application?
So let's say the wide broad use is something that I really would like to dive into shortly. Let's say virtual prototyping, I think, is happening quite a lot. You have free of charge SPICE simulators. You can have SPICE models from the vendors. And I think this is broadly used in the industry. What is not broadly used are really accurate models, considering the package parasitic effects or the implementation on the board. And here, as mentioned, let's say it's really depending on your implementation and the volume of your specific implementation you run as a company, because a double pulse test system, a VNA, a curve tracer, and a lot of instruments you need. And on top of that, what I mentioned, expensive test fixtures, if you want to have a real accurate model, they all drive the cost. And so this kind of characterization is, let's say, useful for companies having a high running volume on a particular set of parts. If you have only one, then or let's say a handful of different parts, then it's more useful to use that as engineering services. What Keysight offers, other companies offers, that you order basically a port modeling specific one, and then as you paid for, you don't want to share that, of course, with others, maybe with some key customers. And I think this is a little bit, how to say, slowing down the adoption of that very high frequency, accurate modeling of the ports.
Thank you, Simon. The next question is addressed to Frenetic with regards to the AI-based
may I give
magnetics.
I'm sorry, Bodo. Can I give you a remark to the model questions, to modeling?
Okay.
Yeah, because, well, I would like to address for the magnetics. So there are basically two aspects. The one is the linearization. The other is the losses. The linearization, so-called non-linearization, is actually can be performed by linear-wise, piecewise linearization. The loss is a problem. For the high frequency, there's a thermal effect in beside that, and the mechanism is not well understood, and therefore whatever people tries to do, they don't have any analytic model, and therefore the either spikes, either such kind of very expensive ASICs, they are using the approach is to using those piecewise linearization, which is for the magnetics. So I'm speaking from the magnetics point of view, and would like to address this requirement for the virtual design that works in certain area, but only limited to that area. So this is my remark. Thank you.
Thank
Yeah,
you,
I can
JC.
second that. For magnetic models, it's very difficult to have respective mathematical descriptions which reflect also the physics. Because if they are, how to say, just reflecting the measurements, then it might be that you have an over-determined system. So this is really something where the industry has some work to do. Yeah.
Okay, thank you, Simon. Now we come to the frenetic questions, which ask specific to the magnetic designing tools presented by Frenetic. What are the features specifically dedicated or optimized for high switching frequency operation?
Okay, yes. I'm not sure I understand properly what that means, but right now, so what I understand of the question, right now we are able to design transformers, inductors, and common mode chokes are soon to come. And when designing these magnetics, we predict like their parameters, their behavior. Instead of using analytical models, we use artificial intelligence models that we train with reality. So that means that we are able to predict losses, core losses, and AC resistance, and the winding losses, the temperature, inductance, and leakage inductance. And we can do that right now for, as I said, transformers, inductors, and especially flybacks, common mode chokes, and we can design with solid wires, lead wires, foils. So I hope that that answered the question.
Okay. Let's go to the next question, which is coming back to Keysight. The comment on the advantage of using Keysight electromagnetic modeling tools in comparison to well-known ANSYS electromagnetic tools. I have nobody from ANSYS here. It would be nice. Now it's just Simon who can make a comment, or any of the other presenter
I
may
try to be
know.
pretty fair because I think it's not okay then to talk about competition, but I worked some years for ANSYS, so I know a
Yeah.
little bit. I would rather go away from the company names. The one, and then talk a little bit about the solution offering. From Keysight, the solution
That's a good way.
is well known to be integrated in device characterization with IC grab and all the test and measurement tools we have and the equipment we sell. This is not, let's say, there on the ANSYS side. On the other side around, we are once focusing on flow and integration and easiness of use. ANSYS has very strong solvers, meshing technology, solving speed and that kind of stuff. So they are also very good and very accurate. You might need to dive a little bit deeper into the theory of FEM and using the tools and that kind of stuff. But I think the most different between the two things is that if, and this is really independent of the vendors and the tools, do you think and talk about resistor, inductance and capacitance if you want to characterize the device, or do you if we go to fast switching speeds, think in the frequency domain talking about S parameters? And if you want to fit a RLC circuit, a tank circuit with many ladder structures and couplings and active devices inside to a broadband response in the frequency domain, you will see very fast that you are limited and that you run into transient convergence problems in the simulation. That's the trade-off between the two approaches, I would say. Either go fully in the frequency domain, what you can do with both tools, parties offering these tools, and many others on the market as well, or do you, let's say, model in the frequency domain and want to have a more accurate model?
Thank you, Simon.
Can I make a remark, Bodo?
Go ahead, JC.
So I would like to address the point with FEM, finite element modeling. This is very widely used. I think it is also very efficient. The problem with magnetics is that the assumption should be structure homogeneous, magnetic isotrope, and that is not the case. And I take the example like ferrite. Ferrite is an IC integrated circuit. If you take a look at the boundaries, is like isolator. The grains like a conductor. So the conductivity, it's a range of 5 orders difference. And this time I did the presentation with demo devices is a metal alloy powder core. This is another mystery. If you take a look on these metal grains, there's permeability like 100,000. And then if you isolate it with a mineral inclusion, then it's going to be used as a low permeable materials. And how is it able to model this with FEM? If you say this is a homogeneous material with a low permeability, it's simply not true. And that's in the majoring drawbacks. I mean, if you take a look to utilize FEM to model these magnetic materials. And that, therefore, I think the most problem is that once it's concerns to the losses, then there are so many things which is not understood, and therefore it's hardly possible. And that previous question, the answers is good tools, and Keysight is instrument, and the instrument is a part of measuring systems, and that's I think that's a lot of things which is it with artificial intelligent designs, which is to emphasize again that's not everything is true is known, and this therefore it makes us a challenge also for the wideband gap application conference. Over, give back. Thank you.
Thank you, JC.
Yeah, just
We
if
got
I
a
may also-
question to Frenetic.
Okay. Just if I may also say, just to remark also what JC said, that for us, and we believe that the real way of going forward in the future with magnetics is measurements, and sometimes you need a model that is able to understand all those anisotropies and to understand that the ferrite, for example, is not homogeneous. That's why we do what we are doing. That's how we train our artificial intelligence. We teach her these anisotropies. So I think there's a lot that can be done still. We are doing that. But as Jay says, and this is just the beginning. Thank you.
Thank you. The question to Frenetic is aging of magnetic materials taken into account in the artificial intelligence sizing, especially for common mode chokes?
For common mode chokes, in those cases, what we do is we take the information from the manufacturer. So it's something we want to include in the future, but it's not. It hasn't been the lowest hanging fruit for us. So we take it into account,
Thank
but
you.
just not as artificial intelligence. Thank you.
So
Thank you, Alfonso.
can I give a remark, Bodo?
Yes, please.
The aging problem is related to the specific parameter
This is not understandable for me.
called disaccommodation. The disaccommodation factor to use a metallic like nanocrystalline materials and with a higher Curie temperature over 600 degrees C, you still have some aging effect, but much less. The problem is, I guess, is much more coming from the reliability requirement. People want to have not only transient efficient effect, they want to have this for a long time. So the reliability is a things which is which is challenged, and that's the thing that the simulation can give some typical behavior, but in the industry we're going to talk with the limit value. The typical value and limit value, that makes a difference nowadays, either in components or to illustrate a typical behavior. And that's make the things, I think that's it's very challenging, and that's all the end users appreciate these answers, but this is still need to get proved. Thanks. Over.
Thank you, JC. We are facing the last 5 minutes. I do not see additional questions coming in. And I think we had a quite good open discussions on our subjects. And I like to thank you to the presenters and to the people from the auditoriums who have raised the questions. Thank you, and looking forward to see you all next year in reality back in Munich at the conference. Take care, stay safe, and Merry Christmas.
All the best.
Thank you very much, Bodo.
Bye-bye.
Thank you very
Thank
much.
you.
All the best.
Very good organizing.
Until next year in person.
Bye bye.
See you. Bye-bye.